The first one waveguide loss we will discuss is scattering loss. The scattering loss has two types. One is Fallon scattering. The other is surface scattering. We first discuss Fallon scattering. Consider an optical waveguide, as I plotted here. During the fabrication, there may be some impurities and crystal defects. And this impurity will make scattering of the propagation wave. As the wave propagate along the waveguide and hit the scattering center, then some of the energy will be scattered out, and then they cannot reach the end of the waveguide, which will induce the waveguide loss. Such kind of waveguide loss, we call it Fallon scattering. And these points, we call it scattering center. Which is formed by impurities. During the fabrication, or crystal defects. The impurities or crystal defects during the fabrication process will form small points in the optical waveguides, and then the EM wave will hit this small point or the scattering center, and some of the light power will be scattered out from the optical waveguide. And usually you can know the size of the scattering center. Suppose the size of the scattering center is D. As the size of the scattering center is much smaller than lambda, then the Fallon scattering can be ignored. On the contrast, if the size of the scattering center is almost the same as the wavelength, then the Fallon scattering will be very serious. You have to take it into account. The other kind of scattering loss is surface scattering loss, which is caused by surface roughness. Due to the fabrication technique, sometimes you cannot have a very planned interface between two materials, and you will have some surface roughness at the interface. As a result, as a light wave hit the interface to induce the TIR, total internal reflection, some of the light energy will be scattered out from the core region. This will induce waveguide loss, and such kind of waveguide loss we call it surface scattering loss. Consider an optical waveguide of thickness Tg in a length of L. The number of reflections from each interface can be obtained by we denote the number of the reflection from each interface is N sub R, which can be obtained by L divided by 2D. The D is here, so 2D means this distance. Okay, and the D value can be obtained by Tg times cotangent theta m, where theta m is the angle is the angle with respect to the waveguide axis as the optical waveguide mode propagates along the waveguide. Okay, so take this value into here. The N sub R can be written as L divided by 2Tg times cotangent theta m. As we have known, the NR can be expressed in this way. So for higher order waveguide modes, we know that as the waveguide mode propagates along the optical waveguide, the K vector will have an angle theta m with respect to the waveguide axis. And as the mode number m increased, then we will have larger theta m. So for higher order waveguide modes, the theta m is increased. As a result, cotangent theta m will be reduced. Then the number of reflection from the co-cladding interface will be increased. Then we will have higher surface scattering loss. Okay, for example, consider an optical waveguide formed by TA205. If we set the operation wavelength to be 0.632 micrometer, and for M0 modes, we have the scattering loss is 0.3 the inverse of centimeter. But for M3 modes, the higher order waveguide mode, we will have the scattering loss is 2.8, the inverse of centimeter. So as the Moore order is increased, we will have higher surface scattering loss due to we will have larger number of reflection from the cold cladding interface.